Okay, so now that we've warmed up, let's now talk about something like this. What do you see in this integral? On top I have a polynomial. Underneath I also have a polynomial. Do you see that? It's not a simple linear polynomial. If I try to do a u substitution and let u be x squared minus 2x minus 3, what is du? 2x minus 2. Do I see a 2x minus 2 on top? So u substitution doesn't work nice with this. Does that make sense? So we are in a situation now where we're going to learn the very last integration technique, and most students in Calc 2, this is their favorite technique because it's all algebra. There's no trig. There's like zero, almost zero, a little bit of trig, but very little trig. Okay. So people like it because it's all algebra based. What we have is a fraction or a rational expression. So I have ratios of polynomials. And when you see the pattern of a ratio of polynomials, by the way, do you guys know what polynomial means? It means many terms. Polynomial means many terms in Greek. There is a polynomial on top and a polynomial on the bottom. In fact, on the top, I actually have a binomial because it's two terms. On the bottom, what do I have? I have a what kind? It is a polynomial, but there's a special kind because I have three terms. What do we call those? Trinomials. Is that what you said?
You know, that's totally right.
That is totally what you said, right? A trinomial, like a tricycle has three wheels. A trinomial has three terms. You see my three terms in the bottom. So I've got a binomial, but it doesn't matter. I just like math, so I like to point out things. What'd you say, Jaden? Trinomial? Okay. So when you see polynomial on top of polynomial, and you can't use a u substitution, all right, then you're going to use this idea of partial fractions. And the goal of partial fractions, let me just tell you what the goal is, because it's nice to understand what our goal is. Our goal is to break up the ratio into smaller fractions. So it's to break up the ratio into smaller or simpler fractions. That's the whole goal with partial fractions. We're going to break it up into smaller ones. And so we have a series of steps that we do to get there. So you ready for our steps to get there?
I'm kind of mad that we're not taking it on like its full force. I'd rather take the whole thing on. Like, are you saying that we can't do a big fraction?
I am saying, I love it. I love your excitement and your energy and your passion. I am so with you. Don't worry. By the end of today, you're going to be really excited. Tina, thank you, because I know I'm going to see this one powerful one on my test next week. Just wait. I know. So, but we're going to make it simpler, and then it'll get harder. You'll see. So we're going to break it up and make it smaller, all right? Just because we can, and algebra is a little better than making bigger stuff. So here we go. Step number 1. In order to break this up into smaller parts, we have to figure out what two fractions add up to make this big fraction. That's our goal. This is going to break up to get two smaller fractions to get big fractions. So you know you're going to have to deal with denominators and least common denominators when you talk about fractions, right? So your first job is to make that denominator simpler and write it as a product. So what is the very first thing we need to do in this? We want to factor. We want to factor that denominator because our goal is to break it up into smaller fractions, and we need factors to do that. So step 1, in order to get to our goal, step number 1 is to factor the denominator. That's step 1. Factor the denominator. Alrighty, can you guys help me factor this denominator? What's x squared minus 2x minus 3? Yeah.
X minus 2, X minus 1.
Close. X minus 3, X minus 3. Yep, X minus 3. X plus 1. Thanks, Grant. You did very good. Very nice. X minus 3, X plus 1, right? X minus 3, X plus 1, because two numbers that multiply to negative 3 are negative 3 and 1, and they add to give me negative 2 in the middle. Beautiful. X minus 3, X plus 1. That's step 1. Step 2. I am going to rewrite this fraction into smaller fractions using variables to help us. So I'll just put A, B, C, etc. to help. What do I mean by that? So I'm going to take this ratio of two polynomials and I want to rewrite it as a sum of two smaller fractions. And I know from my adding and subtracting of fractions that least common denominators and denominators come from smaller factors. And so I'm going to, no, undo that, Tina. So what I'm going to do is break this big thing up into two smaller parts, one of which has a factor of x minus 3, and one of it which has a factor of x plus 1 in the denominator. So this actually comes from adding up two fractions that have x minus 3 and x plus 1 in the pieces. What do I mean, right? So if I'm trying to get, let's just say I'm trying to get 6, well, that actually can come from, like, if I have 5, 6, and 4 halves or whatever, I get a common denominator of 6, right? You see what you know what I mean? To add up fractions, you have to find a common denominator. How do you get common denominators? You come from multiplying things together. So the idea is we got two algebraic expressions, add them together means I have to get a common denominator, which is this sucker here. So I'm going to go backwards and break it up and make it simpler. Now, I'm going to say, I don't know what's on top here yet, and I don't know what's on top here yet, right? To add these up to give me 5x minus 3. And that's where I'm going to use just a placeholder. And that placeholder is just going to be a big letter. So I want the big letter A to hold the place here, and I want the big letter B to hold the place here. So I'm looking for A and B, so that when I add these up together, I get this. That's it. So that's step 2, rewrite as to smaller fractions. And step 3, of course, is to find A and B. Okay? So step 3 is to find A and B. It doesn't even use any calculus. It doesn't use any derivatives. It uses algebra. All we're going to do now is use algebra to find A and B. Are we okay so far? See the big goal. We're taking a big complex fraction. We're making it into smaller fractions. I am going to make for myself a little thought bubble because I'm going to do some thinking right now. And I'll put this right here off to the side. I am going to do some thinking. I might need more thought space, but let's just start with this much thought space. Okay, so I'm going to do some thinking. How do I get A and B? Well, let me see. 5x minus 3, x minus 3 times x plus 1. I want that to equal A over x minus 3 plus B over x plus 1. Now, the last class opted for the shortcut method. Do you guys want the shortcut method or the long method? Shortcut. Okay, all right, we'll do shortcut. Ready? All right, here we go. How do I get A and B? I don't know, but one thing that might be good might be to clear out. People like to work better when we don't have denominators. So is there a way that I can just clear those denominators out? multiply both sides of my equation by something. See, I have an equation, right? I have an equation. So one thing that I can do, there's lots of things I could do, but one thing that I could do really fast and really quick, that's a shortcut kind of, is get rid of those bottoms. How do I get rid of the bottoms? I multiply both sides of my equation by the least common denominator. What is my least common denominator? X minus 3 times x plus 1. Y'all with me? So let's multiply both sides of my equation by, oh, Tina, I'm going to skip a step already. Multiply both sides of my equation by x minus 3, x plus 1. Why is that good? Because that's so good because over here on the left side, right, it cancels it right out, doesn't it? It just cancels it right out. I'm allowed to do it because I have set these two expressions equal to each other. And over here on the right, you should be distributing, right? Because you have a plus here, don't forget to distribute. Most students love algebra compared to calculus, so they're like, okay, give me some of this. This is cool. 5x minus 3 equals a over x minus 3 times x minus 3 times x plus 1, and then plus b over x plus 1 times x minus 3 times x plus 1, because I'm multiplying in by x minus 3, x plus 1. And do you see those also cancel, right? Those denominators on the right side will also cancel like they did on the left side. I'm putting an extra step in. Some people kind of skip this step and try to do things in their heads, and that's okay as long as you guys are careful and rigorous and detail-oriented and get the right things happening. All right. Now, did I do that right? Are we looking good? Does everybody match me? Okay, at this point, there's a couple ways to solve. The first way is to say to yourself, well, one thing I could do is I could put my x terms together, I could put my constants together, and I could equate the two sides. That's one thing you can do. You get a system of equations with two unknowns, a's and b's. Put my x's together, put my constants together, and equate both sides. That's one way to do it. Another way is kind of the shortcut way, which is going to be smart. I'm trying to get big A. I'm trying to get little b. What would happen, guys, if I actually put a 3 right here? I'm just looking here just because I want to look here. What would happen if I put a 3 here? What would happen to 3 minus 3? That becomes 0. And then the b goes away, and so then I can just work on solving for a. Are you with me? So I'm going to put my thinking cap on right now, and I'm going to say, okay, there's a lot going on. Let me focus on just one letter to find. Let me find the letter A or the letter B. To find the letter A, I'm going to have to put a 3 over here. What do I put in the first one then? What should I put in the first one? If I put a -1 in the first one, then what happens? That drops away, and I can find B. Are you with me? Oh, so I'm going to use my brain, and so I'm going to say, let's let x equal -1. See, I'm thinking, right? I'm thinking smart here. Now, what is this in mathematics? This is an equation. X's is simply a placeholder. It's a variable, which means it's a placeholder for a number. So if I want to put -1 right here, strategically to make this go to 0, I just have to put -1 everywhere I see an x. Are y'all with me? Okay, so that means that 5 times -1 minus 3 would have to equal A times -1 plus 1 plus B times -1 minus 3. The logic being, I'll get rid of my A because negative 1 plus 1 is 0, so that whole term goes away. And what does that mean I have negative 8 equals negative 4b. Is that what you guys got? And so then did you divide by negative 4? And so what value are you getting for b? 2. Now you don't have to do it this way, but students tend to like this. They just like this, where they find the thing to make it 0, plug it in, and solve. So by the same token, can you also get me a? Let's see. So let me do the other side. Expand my thought bubble. Thought I might need to expand it. Okay. So now I think I'm going to let x equals 3. And then I have 5 times 3. I'm putting 3 everywhere I see an x in my equation. That's good because I have b times 0, which drops out. What's that giving me now? 15 minus 3 is 4a. 12 is 4a. What'd you guys get for a? 3? More important is the math, is the logic behind why I decided to do what I did, right? I get an equation. It's got 3 unknowns, a, b, and x. In mathematics, in order to get a unique solution, you actually can't solve for a, b, and x with one equation. You'd need 3 equations to solve. Two variables needs 2 equations, 3 variables. You'd need 3 equations to get those specific values for x, a, and b. But we're playing around with it, and we're going to say, well, let's rig the system. Let's knock it down. Let's put in a number for x, because we're allowed to do that, and let's figure out what a is going to be and what b is going to be, okay? All right, any questions on step 3, which is find a and b? Step 4. What do you think step 4 is? Put those numbers back into my original, right? So step 4 then is going to simply be replace those numbers. So step 4 is going to be substitute those numbers and integrate. All right, so I have the integral of a over x minus 3 plus b over x plus 1, and I'm going to be replacing a with 3 and b with 2. And so I have achieved my goal. Do you see that, Jaden? Now I have something. Look how nice that is to integrate. I mean, you gotta say, oh my God, look at that. That's so easy. I have a sum of 2 simple ratios, right? So I can integrate each one separately. So let me put this extra step in. A lot of students will skip this step, but let me put this extra step in. So I'm just going to separate, right? As long as they're added, I'm allowed to separate these 2 integrals. And while I'm doing that, I'm going to go ahead and put my 2 in front and my 3 in front, right? Yeah. It should be x minus 3. Thank you. Thank you, thank you, thank you. Good eye, Yusuki, good eye. You are not sending that NASA spaceship the wrong place. You heard about that, right? About the detail with the NASA. I told you about that, right? Where there was in Florida a NASA spaceship, and some NASA engineers were off by a 0.01 centimeter or millimeter, I forget what it was, but it was like a 0.01 centimeter calculation. But when they sent the ship, because of that little calculation here, when they sent it off into space, it multiplied because of the distances it had to go to, and it missed the target. And we spent billions of dollars on this little satellite, and it missed its target because of a little multiplication decimal place error at the beginning. Those guys got fired, right? I'm sure, right? But I mean, detail. I mean, really happened in real life. I'm not making this up. It happened. NASA, anyways, whatever. So we got it. Thank you for picking my detail out, Yusuke. Thank you. Okay, how do we integrate this, Jaden? Help me out here. 3 times what? Antiderivative of 1 over x minus 3.
That is 1. Oh, wait. ln times x minus 3.
ln of
Absolute value.
ln of the absolute value of
X minus 3.
x minus 3. Do the next one for me too.
Well, it's the same thing.
I want you to say it though.
ln.
The ln.
Value of x plus 1.
Thank you. Beautiful. You guys see it? Oh, wait, that was step 5, right? Step 5 was to integrate, which we already did. So step 4 is replace those values and integrate. Yep. Pretty easy, right? So what's the goal when you have a polynomial of a polynomial? You want to break it up into smaller fractions, smaller ratios. How do we do that? We use some algebra. This is a think bubble. It's not always clear. Sometimes you have to do a little extra work. Then put them back in, and these will always be simpler than what you started with, okay? Ideally, it's just really simple. Any questions? How are yous? Everybody's good? So I want to, you are 100% allowed to do that. So what AK said is he does a different way, and actually this is exactly how I normally teach it. So if you go online to Canvas and you want to see a different way to solve these, my videos from previous semesters have been that way, right there. Some students are seeing this quick trick and they like it, so I thought, well, I'll try it this time. What AK said is an alternative way, rather than picking a number and plugging a number in, is to instead expand both sides of this equation right here. And then notice that A and B are both paired with the x, and the other things are not. And what that allows you to do when you make that observation is now you can create 2 systems of equations, because A plus B, the number in front of x, has to be 5. And A minus 3B, the coefficient, has to be negative 3. And if you like systems of equations, then that allows you to create a system of equations and you can solve it. That is generally the method that I like to use all the time. But some people tend to like just plug the numbers in and get the variables quicker. So it's completely up to you how you like to solve, okay? Does that make sense? Do you guys kind of see what I did there? So I'll leave both of those up there in notes. And like I said, if you want to see more of these here, this would be in Canvas online. I have old videos. My old videos all do that method. I already factored for you on this example. Here we go. Evaluate the indefinite integral of x plus 16 divided by 2x minus 1 times x plus 5 dx. Integral of x plus 16 over 2x minus 1 times x plus 5 dx. All righty, go to it. And like I said, put any notes you need on your F, right? Put any notes you need on your F if you need for helping and tools and jogging your memories. As you do your homework, jot down things you need. physics. Don't tell anyone. Like U is equal to something, du is something. What du is 2 dx. You see it? Alrighty, so I'm going to put a on top of 2x minus 1 and b on top of x plus 5. And let's see. So then I'm going to do my thought bubble over here because I'm going to put these together. Okay, so over here I've got a over 2x minus 1, b over x plus 5, and that has to be x plus 16 over 2x minus 1 times x plus 5. And I'm going to multiply through by the denominator 2x minus 1 times x plus 5. 2x minus 1 times x plus 5. 2x minus 1 times x plus 5. And I'm going to cancel what I can. This guy cancels 2x minus 1. This guy cancels x plus 5. This guy cancels the entire denominator. So that gives me a times x plus 5 plus b times 2x minus 1 equals x plus 16. Most of you guys did this, so I'll do it this way to start. Most people tried to cancel out the x plus 5 with a minus 5, and so they got a negative 5 plus 5 plus b times negative 10 minus 1 equals negative 5 plus 16, or negative 11b equals 11, or b equals negative 1. To cancel out the 2x minus 1, we need x to be 1/2. So it's a times 1/2 plus 5 plus b times 2 times 1/2 minus 1 equals 1/2 plus 16. That goes to 0. This goes to 5, 10, 11 halves times a, and that's 33 halves. And then I have to clear that out by multiplying both sides by 2 over 11. So that's a is 33 over 11, which is just 3. So did you get 3 and negative 1, Gavin, doing it the other way?
Yeah.
So if you had instead decided to do it the way AK likes to do it, you would get ax plus 5a plus 2bx minus b equals x plus 16. And you notice you have a plus 2b times x, and then 5a minus b. And so you could set up a system of equations. A plus 2b is 1. 5a minus b is 16. And you could solve that system and then get the same thing if you wanted to do it that way. All right, any questions? Did everybody get b negative 1 and a 3, however you chose to solve? So when you went to integrate, you put 3 over 2x minus 1 dx, negative 1 over x plus 5 dx, and you should get 3 over 2 times the natural log of 2x minus 1, and ln of x plus 5. Is that what you guys got? Who's got a question? Yeah, Jaden.
Where the hell did that 2 come from?
Which 2?
The one underneath the 3.
Can you answer that?
Beats me, that's why I'm asking you.
Okay, stop. Slow me down. Hang on. Go to your notes.
Yeah, use my head a little bit, I got you.
No. Go to your notes. Go back 3 examples for the first. We did 4 problems right at the beginning of class. Were you here? Yeah, you were here.
Well, yeah.
Did you write it down?
No, I was not in the classroom, I was too busy.
Oh, Carson, did you write it down? Show him. Where's it at? Oh! When there's a number in front, and you do u is 3x plus 5. The du becomes 1/3. You see, when there's a number in front, you have to flip them over.
I'm good next time. Don't worry.
No, that's okay. You got to do what you got to do. Everybody see? Does that make sense, though? Do you see where it comes from now? Thank you for the question. I'm not picking on you. I really, really want you to see it. Write it down here so that it's in our notes for me. So that's, what would that mean? Yeah. I love it. I like it. Does that make sense? Do you see it? Because that number is in front of the X. Thank you for asking, because I'll tell you what, I'm going to guarantee that you're not the only person that missed it. 1,000%. Yeah, and now you know for the test. Exactly. Mistakes allow thinking to happen. Always. Questions allow thinking to happen. That 2 came from letting u equal 2x minus 1. Okay, that 2 came from that 2 there, and u is 2x minus 1, du is 2dx. The 1/2 du is the substitution, and that's where it comes from, right there. Question, Grant.
If we were to graph the integral, would there be a hole?
Right? Linear factors are things that are like power 1, right? 2x plus 5, x minus 1. Non-linear factors are things like this, where we have x squared plus 16. Are you all with me? Okay. So, what do we do in those cases? We're going to do the same thing. We're going to do the same thing, kind of. We're going to break this up into 2 factors. See how you have an x, and then what's my other denominator? X squared plus 16. But there's a rule that I didn't tell you that is always true. Is when you break them up, you want the numerator to be 1 degree less than the denominator. So when you break up these fractions in order to get 2 simpler fractions to add up together, you want the numerator to be 1 degree less than the denominator. Which means, so for the first one, it's just a linear x, right? It has a power 1 there, so I put a constant a on top. But on the second fraction, what do you see about the second fraction? What's my degree? 2. So I have to put 1 degree less, which is the degree of 1. So on top, instead of just putting a b, I have to write bx plus c. Let's just suppose I had x cubed plus 16. What would I have to put on top? Bx squared
plus cx plus bg.
Yep. Do you see that? So always when you're getting these things and writing this polynomial and breaking them down, we want 1 degree less, okay? 1 degree less as we go. I am going to put a big smiley face here. This is going to be a really nice big problem. Jaden, this is going to be a super beautiful big problem that we're working here. You know, every semester I teach Calc 2, I put one of these on my test. Every semester I teach Calc 2, I put one of these kind of things on my test. Okay? So I put a big smiley face there because you're going to expect to see, I love these problems. This is like a favorite of mine. All right, so here we go. What are we going to do? We've got a over x plus bx plus c over x squared plus 16. You got to make them equal. Guys, get me some values for a, b, and c. Get me some values for a, b, and c. Oh, hang on. Yeah, hang on. Slow me down a second. I'm not quite happy yet. Hang on, I'm not quite happy yet. Because look at that number. This is web work for us, isn't it? Web work does this where they throw these big numbers in here. Okay, I don't like 96. You guys aren't allowed calculators on your test. That's too big. That's too big, right? What could I do to make this integral, Reese? Can I take out a 3 everywhere, guys? Are you okay? Would you allow, let's do this. Let's just take that 3 right on out before we do anything. Because I did that, Grant, because I always say to myself, oh, what if the denominator was x cubed plus 16? So that's a what if question. Do you see what I'm saying? Like if it's x squared, I know what to do. But let's just say on your homework you had an x cubed. Then what would you do? And I was just saying, well, let's do 1 degree less. And what would that look like? That would look like bx squared plus cx plus d. Does that make sense? Do you see? It's actually not part of the problem. Sorry. It was a what if question that I kind of did in my head. All right, wait. What's 3 goes into 96 how many times? 32, right? 32. Okay, so that means I have x squared plus x plus 32 over x times x squared plus 16. And that's going to equal a over x plus bx plus c over x squared plus 16. And I'm going to get a common denominator of x times x squared plus 16, and I'm going to multiply that through everywhere. It's so quiet. You guys are just the greatest class. Can I tell you? It's so quiet. It's a little more complicated because there's nothing I can put in here to give me 0, right? But let's put a 0 here and then put 0 in for x. So let's start by letting, I like your thought there, Jake. Let's let x, oh, you want to expand it, okay.
It is really easy to expand it.
Oh, okay, I'll expand, oh, is it easier if I expand it?
Yeah.
Okay, well, hang on. If I did do this way, Jake, did you get b times 0 plus c times 0? This all went away. Let's just make sure. Did you get 32 equals 16a?
Yes.
Ah, good. And so you got a is 2, right? Awesome. But the problem is getting the other ones, right? Okay, that's fine. Okay, so you guys, so Gavin and AK are saying, well, let's also try to expand it and see what happens. All right, so if I expand it, I have x squared plus x plus 32 equals ax squared plus 16a. You know what? Hang on a second. I could expand it, but all right, I'll expand it. Plus bx squared plus cx. So if you expand it,
You only have one value with like the A 16, and it's only for the 32. So you divide that when dividing 16. Both of them is equal to 2.
I see. So if I expand it, then what happens, that's really nice, when I rearrange my terms, I can rearrange my terms, right? Because I can put my x squareds together and factor out an x squared. So I can put those two together and factor out an x squared, and I get a plus b times x squared. And I have a cx term, and I have a 16a term. And so you're saying, well, Tina, just look at that on both sides. Just look. 32, my constant has to be equal to 16a, which is what you got, Jake. Yep. So that means 32, undo. 32 is 16a, so a is 2.
And now you know since A is 2, and you know plus B has to equal 1.
Okay.
So 2 plus B is equal to 1, so you know B.
Okay, so a plus b has to be the coefficient on x squared. So a plus b has to equal 1. But I already know that a is 2, and so that means b has to be negative 1. 1 minus 2.
And then you know C is 1 because it's whatever the coefficient of the first x is.
Oh.
The second x.
So c is the only thing in front of an x, and therefore, to make it equal, c has to also be 1 to make both sides equal. I like it. I know, confused. So the problem here, Grant, was that x squared plus 16 doesn't ever go to 0, right? You can't put anything in there. Add it to 16, right? Square it. Like negative 4 squared is positive 16. Are you with me?
Yes.
So there's nothing that will zero it out. So instead, what you can do is you can expand out. Do you see how I multiplied out this right side right here?
Yeah.
And if I multiply out the right side, I get this 4-term polynomial. And if we look at it and rearrange the terms, do you see? If you rearrange the terms,
Yeah, but you can't combine 13 and 16. There's an A and it's constant.
ah, correct. Do you see this right here? But if I step back a second, do you see you have an x squared and an x squared? Which means whatever's in front has to be equal. So I can make it equal. There's an x over here and an x over here. I'm just going to focus on the front, the coefficients, and set those equal. And 32, which doesn't have any letters with it, right, has to equal this piece, which doesn't have any x with it. Neither of those pieces have x's, so I can equate those pieces. Do you see? So instead of like doing things over here, another way to look at it is to look at expanding it out and saying, what's in front of x squared? Well, here it's a 1, here it's an a plus b. They have to be equal to each other. Here in front of the x is a c, in front of this x is a 1. They have to be equal to each other. And this has no x's, that has to equal the piece over here that doesn't have x's. It's just another way to think about solving that problem.
Yes, got it.
Okay, we'll sit down and we'll do it later. I'll do another one with you, okay? I'll sit down with you and I'll do it with you, okay? Just put a little note. Tina's going to work this through with me, all right? And I'll sit down and I'll show you. And then you're going to be like, oh, I see it, Tina. That's really cool. I'll show you. I promise, Grant, okay? But what I want you to do at this point, because it's a longer problem, is I want you to write these numbers down for me, okay? And I promise you I will fill this in for you, okay? And anybody else that wants to stay after for 5 or 10 minutes, I will stay after and we can work through one of these. Okay, so now that I have the A, B, and C, I want to take and rewrite this problem. I want to rewrite it as A over X plus bx plus c over x squared plus 16. And in place of a, what are we putting? We're putting 2. And if it's okay with you guys, because I know I'm breaking it up into smaller parts. See, I know I'm breaking this up into smaller parts. I'm just going to go ahead and break it up right here as I go. What was that? Ooh.
The thing is still like negative x plus 1. So.
Yeah? Uh-huh. Like that? Is that okay if I put that there? Did I skip too many steps? Let me replace it. How about we replace it? A is 2. B is negative 1. C is positive 1. There's a 3 in front of everything because I didn't want to deal with the 96. So there's a 3. Are you guys okay how there's a 3 in front of everything? The first integral comes from 2 over x. The second integral comes from taking this denominator and putting it under negative 1x over x squared plus 16. And the third fraction comes from taking that denominator and putting it under 1. Is that okay with you guys? I just thought ahead. I thought, oh, look, I want to get these into smaller pieces, so I'm going to look at each part separately. That's what I said to myself. Maybe I went too fast too soon, huh?
Well, the n is like not so nice because you have an x squared on the bottom and the x on the top.
Thank you. So, yeah, Reese.
Is there an R not in the extra?
Yeah, something like that. You guys are so good. You guys see what to do with the first one, right?
Oh.
Well, the first one, the 2 can come out, right? And it's just a natural law. The second one, what are you going to do to... What are you going to do to integrate that second one? U sub, because if you let u be x squared, du is an x, right? U sub. The second one is a u sub.
Professor,
Yeah.
how are you able to break up that fraction when there's 2 terms in the denominator?
I'll show you why. Because if I have x squared plus 1, watch this, let me show you why. Suppose I had this. I have a common denominator, right? And how would I add that up, Grant? Do you see what I did? I simply took those 2 fractions and put them together, but instead I expanded and made 2 smaller fractions out of it. Now, I'll tell you what, you guys are like, oh my God, Tina, I'm never going to use this in real life. No, you're probably not going to use this in real life. It is foundations for all of science, right? Math is all of science, right? But what you are learning these first 3 weeks in Calc 2 is what is the language of math. What is going on? Can I break up fractions? Is this multiplication? Is this division? Is this composition? And you're looking at finding patterns and using different tools to work with patterns, okay? You're learning critical thinking and the language of math these first couple weeks. Then we get to do rotations. Just wait. 2 weeks, we're going to rotate things and make donuts and footballs and all kinds of cool stuff, all right? But we got to get there, as well as parametric curves and polar curves. But, all right, so you guys are using U substitution right now. That's the tool for this one. What tool are you going to use on this one? It's like an arctan, isn't it? It's like an arctan. But it doesn't have a 1 there, right? But it's like a trigonometric substitution. If you don't know the arctan thing, right? It's like a trigonometric substitution. Do you see x squared plus a squared on there? Yeah, it's like a trig substitution. All right, so I'm going to put a trig substitution. You should get something with arctan when you're done at the back end.
X over 4, R over 4.
X equals 4 tan theta, right?
Yeah.
Yeah, uh-huh. So I'm just going to put, you probably have the answer already, AK. You're probably ahead. I'm going to use you to walk around if people need help. But I would use trig sub on that last one. All righty. Let's get to work. I have 3 integrals. I need 3 answers for those 3 integrals if you don't already have it, okay? This one's a doozy. This one is an absolute doozy. You got it? Wait, you need more space.
I know, but like, I'm almost done with the problem.
Oh, you are almost done with the problem. Okay,
Like, all I have to
okay.
do is the trig subs.
You do. You want to do it over here? You're going to do it right there.
Not really.
Ah, okay.
I'll do somebody else.
Yeah. Just wait for somebody else to get it. Okay. No! No! You need to not sit next to Carson. He is a bad influence on you. X equals 4 tan theta, right? X equals 4 tan theta. Because 16, square root of 16 is 4, right? A is 4. X equals 4 tan theta. What's dx? 4 secant squared theta, d theta. This last one, because x squared plus a squared, you have 16, so a is 4, right? Oh yeah, you're going. Did you get it, Reese? Did you get the arctan?
Yeah.
Yeah? Good. Because the secant squareds cancel, don't they? Secant squareds cancel right out. Secant squared should cancel right out. You should get an arctan, because you got something with an arctan in it, right? Beautiful. And so you're putting in place of x. Or in place of x, you're going to put 4 tan theta. Yeah, no good, no worries. Keep going. Keep working. Okay, Jake, you got this going okay?
Yes.
Okay. And how are we doing? Ooh, almost slipped. Nice. Very nice. Very nice. So 2 over you, right? Because you didn't use up.
No, I would just.
Oh, yes, you did. My bad. I'm so sorry. Yep. Use up. Yep. Which is why you have to do it in a second.
So I just have to.
Good job. Good job. Good job. Good job. So let's see. So let me write this out here. So I've got 6 times the natural log of the absolute value of x plus, nope, undo, minus 3 times the integral of x dx over x squared plus 16. And then plus 3. Okay, so now this middle one, I'm going to let u equal x squared plus 16. du is 2x dx. 1/2 du is x dx. So that's what I'm going to replace. So everybody should be getting 6 times the natural log of x minus 3/2 times the natural log of x squared plus 16 plus, and then you have that other one, right? So then you have your very last piece, the arctangent piece. So I'm going to let x equals 4 tan theta dx equals 4 secant squared theta d theta. Undo. Hang on, Tina. You're getting in a bad space. So now dx gets replaced with this, and x gets replaced with that, and that's going to give me 4 secant squared theta d theta over 16 tangent squared theta plus 16. And we know, because we've been practicing these over and over and over again, yesterday in lab, the day before in class, the lab before that, we practiced factoring out and using our trig identities to simplify. Tangent squared plus 1 is secant squared. So really, that's 3/4 the antiderivative of 1 d theta, which is just 3/4 theta. And so you guys drew your triangle. You said that x over 4 is tangent. And, I didn't even need my triangle. I didn't even need my triangle because theta is simply the arctan, right, of x over 4. So it looks like this is simply 3/4 times the arctan of x over 4. Is that what you guys got? Plus 2 would be a repeated factor. We would write it as x plus 2 squared. X plus 1 to the 4th power would be x plus 1 times x plus 1 times x plus 1 times x plus 1, right? So those are repeated factors. If that's the case where you have a repeated factor, when you go to write it out, you actually have to do this. You have to write it out multiple times. First as a linear and then as a square. Otherwise, things just cancel out for you. You have to do it this way. So like, what if I had 6x plus 7 over x plus 1 to the 3rd power? Well, then I would break it up as a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 to the 3rd. Do you see what I'm saying? So if you have repeated factors, you deal with it by setting it up like this. And then you go through like normal. Okay, then you go through like normal, get your common denominator, cancel things out, and move on from there. Does that make sense to everybody? Yeah, go ahead, AK. Question? Say what? Why is it squared? Because this here is an example of what's called a repeated factor. And if you don't square it, you should try it without squaring it. Like put a over x plus 2, b over x plus 2, and try it. You lose the x terms. You lose terms. So you have to write it this way. You just have to. Okay? You just have to. Difference of cube formula. Hang on. A cubed minus b cubed factors as a minus b times a squared plus ab plus b squared.